Section 2.4, Properties of Quadratic Functions. So the deal is that we want to be able to work with quadratic functions. That is, we want to graph them easily, and we want to gain as much information as possible as quickly as possible. And so to do that, we're going to look at this in two separate ways. Specifically, we're going to look at two forms of quadratic equations. That is, vertex form and standard form. So here I have what's called vertex form. Notice that this is kind of useful because this actually is indicative of those transformations that we've talked about. That is, A is a vertical stretch or compression, H is a left or right shift, and K is an up or down shift. And so the deal is that when we're actually trying to get information from this form, it's called the vertex form because you get the vertex for free. That is, if it's in the form A times parentheses x minus h quantity squared plus K, H, where as long as you change the sign, K is the vertex. So remember that left-right shifts are backwards, so swap the sign for the H part of the vertex and leave the K sign the same. Now we also get this thing called the axis of symmetry, and the axis of symmetry just is where you would split a quadratic function and it would mirror on both sides of that split. And so our axis of symmetry is always going to be x equals the x coordinate of the vertex. This is always going to be true. So for here, it's going to be x equals h. Then vertical stretches or compressions are going to be dealt with via the absolute value of a. Remember that if the absolute value of a is a number bigger than 1, it's a vertical stretch. And if it's a number between 0 and 1, it's a vertical compression. Then for our vertical shifts, remember that positive k is up, negative k is down. Horizontal shifts, backwards, negative h here is going to really make it go right. Positive h here is really going to make it go left. We also can do it in standard form. So if I have f of x is equal to ax squared plus bx plus c, we can find the vertex. But real quick, to tell you how we find the vertex, we actually use the quadratic formula. And since the quadratic formula is actually showing us where the x-intercepts are, it uses negative b plus or minus the square root b squared minus 4ac all divided by 2a. Now I'm going to split up this 2a and say, look, it's really the same thing as negative b divided by 2a plus or minus the square root of stuff divided by 2a. Now why have I written this all down? Because really what's happening is if you can remember the quadratic formula, then you know the center. Because what's happening is the center of a quadratic equation occurs at negative b over 2a, and then the x-intercepts are found by going a little bit to the right using this distance and a little bit to the left using this distance. And so that means that if I'm trying to find the x-coordinate of my vertex, it's really just going to be negative b over 2a. Then once I find that negative b over 2a, I just take it and I plug it back into the function. Plug in the x-coordinate, we get the y-coordinate. And so that's what I've written here. The center, negative b over 2a, is the x-coordinate of the vertex, and then f of negative b over 2a will actually give us the y-coordinate of the vertex. Then remember that the axis of symmetry is that center, so it's going to be x is equal to negative b over 2a. Then we still have this situation where a, in absolute value, is a vertical stretch or compression. Remember that if a is bigger than 1 after we ignore the sign, then it's a stretch, and if it's between 0 and 1 after ignoring the sign, it's a compression. Now when we want to deal with the vertical shifts up and down, technically that's going to be f of negative b over 2a because that's where we actually find the y-coordinate of the vertex. That tells us how much we shift up or down. And then the horizontal shift could also be considered as minus b over 2a and just see which way we go. So for both vertex form and standard form, let's reiterate. If a is positive, then the graph is going to open up. That is, it will look like this. And if it looks like this, then it will have a minimum value. That minimum value will occur at the bottom. And specifically, it will occur at the vertex. So if you're ever trying to find the minimum, it will occur at the vertex. Now if a is negative, that graph is going to open down. And if it opens down, then it has a maximum value up here. And once again, if you're looking for that maximum value, it just will be the vertex. So now let's graph the functions by starting with the graph of y equals x squared and then using transformations, shifts, stretches, compressions, and reflections to get the correct graph. And so notice that this graph does what? This graph goes left 4 and down 2. And so if I go left 4 and down 2, that's actually my vertex. And then because our a is positive, it opens up. And specifically, it will look something like this. Now, this is a sketch. And so I don't claim that I've correctly graphed the x-intercepts, but if you wanted to solve this equation using the square root property, you could definitely find the x-intercepts and get this graph as accurate as possible. But what does matter is that we found the vertex, and that is -4, -2. So consider this one. We want to graph the function. Well, this one's in standard form. And so because it's in standard form, unless you desire to complete the square right now, let's use our shortcut of finding the vertex being -b over 2a, and then f of -b over 2a. So -b over 2a is -6 over 2 times -1. That's really -6 divided by -2, which is +3. And then if I want to find f of -b over 2a, that's just f of 3, which is then going to be -3 squared plus 6 times 3 minus 4. -3 squared, the negative's on the outside, so that's really -9. 3 times 6 is 18 minus 4. That's going to leave us with +5. And so now I know that my vertex is the value 3, 5. Well, since I now know the vertex, I can go to 3, 5 and plot the vertex. Then we don't have any vertical stretches or compressions. There is an A, but it's 1, so there's no vertical stretches or compressions. But notice that there's a negative out front, which means that this thing must open down. And so if I wanted to open it down, I know that this thing will look something like this. Once again, this is a quick sketch. If we wanted to get it more accurate, we would need to pick values for x, plug them in, and get a few points to find this. Or we could find our zeros by completing the square, or using the quadratic formula. So now if we have the quadratic function, f of x is equal to x squared plus 2x, let's answer all these questions and get a pretty good graph. So first off, does this function open up or down? Look at the leading coefficient. Is it positive or negative? It's positive. Since it's positive, this thing opens up. Then we ask ourselves, is this in vertex form? And the answer is no, it's not. So we need to find the vertex. Make sure it's in standard form, which it is. Then we can find the vertex by taking -b over 2a, which is -2 over 2 times 1. That is -1. Then we can plug that back into the function. F of -1 is going to give us -1 squared plus 2 times -1, which is 1 minus 2, or -1. And so our vertex is now, we know, -1, -1. Once we have the vertex, we get the axis of symmetry for free. That's going to be x is equal to -1. Understand that axis of symmetry is always going to be a vertical line for these functions. So x equals whatever the x-coordinate of the vertex is. Then if I want to find the x-intercepts, well, let's solve this thing. Pick our favorite method. I see that this is x squared plus 2x is equal to 0. I'm going to factor this. X times x plus 2 is equal to 0. I think this is the easiest. Then we get that is equal to 0. Then zero product property, x is equal to 0, or x plus 2 is equal to 0. That gives me x is equal to 0 and x is equal to -2. And so I get two x-intercepts. They are 0, 0 and -2, 0. The y-intercepts, we just plug in 0. F of 0 is equal to 0 squared plus 2 times 0. Well, that's 0. So the y-intercepts are 0, 0. Once again, anytime you have a function, if your x-intercept is the origin, you know that the y-intercept must also be the origin. Now let's graph this function. So we know that the vertex is -1, -1, and we know that the x-intercepts are 0, 0 and -2, 0. And then I can plot this and it looks like this. Pretty close. Be careful, this is not sharp at the bottom, it is curved. The only sharp functions that we're going to deal with are the absolute value function. Then we need to find the domain, but if you consider algebraically, the domain here is all real numbers because we don't have division by a variable or even index radical. Then consider the range by looking at the graph. Take your horizontal line, drag it up, and ask when's the first time you touch the graph. The first time is at -1. It does exist, so it's included. So from -1 up to positive infinity. Then we need to list when is this thing increasing and decreasing. Notice that it's increasing from the x value -1 to infinity. Because -1 exists, we're going to use a bracket. Then where is it decreasing? It's decreasing from -infinity to -1. Once again, because -1 does exist, we're going to use a bracket. We have the quadratic function f of x is equal to -x squared minus 4x minus 4. This thing opens down because we see that the leading coefficient is negative. Then the vertex is -b over 2a, or -4 divided by 2 times -1. That's going to be +4 divided by -2, which is -2. Then f of -2 will give us the y-coordinate of the vertex. That is -2 squared minus 4 times -2, minus 4, or minus 4 plus 8 minus 4, well, that's 0. And so our vertex is going to be negative 2, 0. Thus, our axis of symmetry is x is equal to negative 2. That is the x-coordinate of the vertex. Our x-intercepts, I'm going to choose to factor again. So this is 0 is equal to, I'm going to factor out that negative 1 first. Negative times x squared plus 4x plus 4. And I see that this is actually a perfect square trinomial, or negative 1 times x plus 2 times x plus 2. Specifically, use the zero product property. That is, x plus 2 is equal to 0. Technically, negative 1 equal to 0, but that gives us no solution. And then x plus 2 is equal to 0, but we don't care about the repetition. So then when we subtract 2 from both sides, that's going to give us x is equal to negative 2. So now we know we have one x-intercept, namely negative 2, 0. Now notice that our x-intercept was actually the vertex. And honestly, anytime you find the vertex and discover that it is an x-intercept, you know that it's going to be the only x-intercept. And really you can think back to the discriminant stuff. That is, if you have a vertex on the x-axis, it's the only x-intercept. Then to find the y-intercept, we just evaluate f of 0. But f of 0 is going to be negative 0 squared, or 0, minus 4 times 0, or 0, minus 4. And so our y-intercepts are 0, negative 4. Now I think we have enough information to graph this. We have the x-intercept negative 2, 0. That's also the vertex. And then we get the y-intercept 0, negative 4. And due to its axis of symmetry, I know that there's another point, 1, 2, 1, 2, to the left of the center. And so I know now that this quadratic looks like this. Once again, this is not sharp, it is curved and smooth. The only sharp one is absolute value. Then to consider the domain, notice that we don't have any division by a variable and we don't have any even index radicals, so our domain is all real numbers. Our range, notice if we start from the bottom and we move our way up, we are touching everything way down there at negative infinity. And then as I drag my way up, when do I stop touching the graph? And I stop touching the graph after 0. So I get to 0, but I include it because it really exists, and then I don't touch anything anymore. Then for increasing, notice that we're increasing from the x values negative infinity up to the x value negative 2. It does exist, so we're going to use a square bracket. And then it's decreasing from square bracket negative 2 because it does exist up to positive infinity. Now let's say that we want to find the quadratic function for the graph that's given. And so if we want to do this, let's just recognize some things about quadratic function. This thing has a vertex. Here it is. Now the problem is if you notice, it doesn't end up on one of our nice tick marks, so we're going to have to do some calculations to find it. But I do know that it's true that there's this axis of symmetry that runs through that value. All right, great. Well, notice that this point and this point are on the same horizontal from each other. And since that's the case, if I wanted to find the center of that, I could find the midpoint. All I really care about is the center of the x's. But we'll just write down the midpoint formula. And so that is x1 plus x2 divided by 2, and y1 plus y2 divided by 2. We're just finding the averages. That's going to be negative 1 plus 3 divided by 2, and 1 plus 1 divided by 2. But that's going to give us 2 divided by 2, or 1. And 1 plus 1 is 2 divided by 2 is 1. So my midpoint here is the value 1, 1. Now the beauty of this is that now I actually know the x-coordinate of my vertex. It's 1. It's not perfect, but we're on our way. And since we're working towards this, let's go ahead and write down our vertex form of a quadratic. That is, f of x is equal to sum a times x minus h quantity squared plus k. Well, notice that now I have my h. So if you want, we can start filling in the blanks. This is x minus 1. Now we don't know k and we don't know a yet. Still figuring those out. I'll erase k and a as we find them. But now the question is what could we do? Well, I know a trick. And that trick is if I can get two equations that are linear with two unknowns, I can find the answers because I have two unknowns. So now let's use what we know about functions. That is, if I take and I plug in a value into the function, I get some output. But those inputs and outputs are really ordered pairs that show up on the graph. And so if negative 1, 1 shows up on the graph, why don't we say f of negative 1, I know that equals 1. And then I'm going to use what I've written up here, a times x minus 1 quantity squared plus k, but I'm going to plug in negative 1 for x, that is a times negative 1 minus 1 quantity squared plus k. Well, that gives me 1 is equal to a times -1 minus 1 is -2. -2 quantity squared is +4, so that's 4a plus k. All right, now we have one equation with two unknowns. Let's do it again. Let's use another point. We could use 0, -5. And so f of 0 is equal to -5. That is equal to a times 0 minus 1 quantity squared plus k, which gives us the equation -5 is equal to -1 from 0 is -1. -1 squared is +1. That's really a plus k. Now we have two equations, two unknowns. Pick your favorite method to solve two equations, two unknowns. I see that if I've got this one and this one, I could just subtract them and the k's are going to go away. So how about I do 1 is equal to 4a plus k, and then subtract the equation -5 is equal to a plus k. Remember, we're subtracting each one of these pieces, so I do have to distribute that negative, so this is really 1 plus 5, which is 6. 4a minus a is 3a, and then k minus k is 0. And so that is, I get 6 is equal to 3a, and since 6 is equal to 3a, I can solve that a. Divide by 3, a is equal to 2. Great, I found more, so now I know that the coefficient there is 2. Only thing left to find is k, so pick one of these equations, throw the 2 in. I'm going to choose this one. So that is -5 is equal to 2 plus k minus 2 minus 2. That is -7 is equal to k. And so now I have k. I can replace k with -7, so plus a minus is really -7. And we're done. We have now found the function. That is, f of x is equal to 2 times x minus 1 quantity squared minus 7. And we found our vertex to be -7. So now let's determine whether this graph has a minimum, a maximum, and then figure out what that maximum or minimum is without actually graphing it. So step 1, look at the leading coefficient. Notice that the leading coefficient is -1. Since it's -1, I know that this function opens down. And honestly, I'm just going to sketch it and say I know that it looks like this. That means that I know it has a maximum value. It's got to have a maximum. And if we want to find that maximum value, remember that that's really just the vertex, and so we can find the vertex since this is in standard form. That is -b over 2a, or -30 divided by 2 times -3. That's going to be negative times negative on top is positive. So that's 30 divided by 2 times -3 is -6. 30 divided by -6 is -5. So then to actually find that maximum value, we need to calculate f of -5. f of -5 is -3 times -5 quantity squared minus 30 times -5 plus 7. -3 times -5 quantity squared. -5 quantity squared is 25. 25 times -3 -75. Then we have -30 times -5, which is positive 150, plus 7, and that's going to give me positive 82. And so I've actually found its maximum. The max is equal to 82, and that happens at the x value equal to -5. So remember that you could answer it one of two ways depending upon the way the question is phrased. The maximum is 82. It occurs at -5, but the ordered pair is -5, 82. The marginal cost of a product can be thought of as the cost of producing one additional unit of output. For example, if the marginal cost of producing the 50th product is $6.20, it costs $6.20 to increase production from 49 to 50 units of output. So let's suppose the marginal cost C in dollars of producing X thousand MP3 players is given by the function f of x is equal to x squared minus 140x plus 7,000. How many MP3 players should be produced to minimize the marginal cost? Well, first off, consider that this is just a quadratic function, and so really if I were to sketch that, because I see the leading coefficient is positive, I know that this function looks like this. And since it opens like this, we know there exists a minimum value specifically at the vertex. So that is, we just need to find the vertex to answer this question about the minimum. So -b over 2a is equal to 140 divided by 2, or 70. Then if we want to minimize the marginal cost, understand that marginal cost is really the output f of x. And so now I just need to evaluate f of 70. F of 70, that is 70 squared minus 140 times 70 plus 7,000. Just do the arithmetic, and what are we going to get? I get 2,100. And this output is in dollars, and that is the minimum marginal cost would be 2,100. Notice that we also want to know how many MP3 players would need to minimize that marginal cost. That is 70 MP3 players.